So in this video, I want to help you solve one of our homework problems. It's also a great example problem about the usefulness of exponential models and how they can help us answer certain questions. So the problem prompt is given above, and just to give you the big idea, basically if you take a drug, whether it is prescribed or recreational, over time it will be decaying in your bloodstream. And this is why if you take Tylenol, if you read the back, it says wait 4 to 6 hours until you have your next dose. So behind the scenes, biologists and mathematicians have worked together to kind of come up with a reasonable time when it's safe to take another dose. So in this problem, you're given some initial information, and I just want to kind of point out to you what this is really saying. So initially, there's a certain amount of concentration in your drug, in your body, and just so you're getting a sense if this is time, and they're giving us the units as hours, and then the other information is the concentration in your bloodstream, and the units of concentration are given as milligrams per liter. So what I've underlined in pink is really saying initial concentration means time is 0, that you have 20 milligrams per liter. So that's really giving us a point, and the point is a y-intercept. Okay, now the other piece of information that we're given is 3 hours later, we're at 12. So I won't draw this to scale, but the thing that you want to think about is there's this other data point, and I'll label it 3, 12. And then we're also being told that the overall type of model we're using is exponential decay, and in part A, they're giving us an actual formula for it. So that is telling us that we're looking for a function that goes through these points and has an overall shape like this. Okay, so our first task in part A, they're giving us the form of the model. So C stands for concentration, and that depends on time. And we're being told it's equal to C sub 0, that's the initial concentration, times e to the kt. And we can also point out that because this is a decay problem and the shape of the graph, the height of the yellow curve is getting lower as time goes on, I already know that the k is going to be a negative value. We'll still need to solve for it, but that's a good check for reasonableness when we start. Okay, so what we can do is we can use the first point that I've used pink for, and I'm going to just put in the values of the pink. So when time is 0, this is equal to 20. And this should actually be like that. Okay, so what this is saying is we know any number raised to the 0 power is 1. So this term is becoming 1. So we have C sub 0 times 1 is 20. And this is the same as giving C sub 0 is 20. Now, a shortcut, if you don't want to do this, is that the C sub 0 value is always just the y-coordinate of your y-intercept, or the initial amount. But what I've done with this bullet point, this will always work. You're basically using that pink point to figure out the value of the C sub 0. So what that means now is I know a little more about my specific model. Instead of C sub 0, we can just put the number 20 in, and I have e to the kt. Now, there's one other point that was given, the blue point. So what I'd like to do now is I would like to use that information, and I'll switch to blue so you're seeing what's happening. I'm going to put the 3 in everywhere there's a t, and then the value has to equal 12. So again, those numbers came from this blue point, and that blue point came from the second piece of information given in the problem prompt. So now our job is going to be solve for k. Okay, so this is going to take just a couple steps. I think I will flip the slide for you so you can see how this is going to work. Okay, so we have 20 e to the k times 3 is equal to 12. And we got that equation from the blue point, and our job is solve for k. Now I just want to make the note that k is like trapped up in the exponent. So we'll need a way to get it down. And luckily, there's a very convenient way that we've learned about in this class, and it's a logarithm. And the reason a log will do this is, if you recall, the third property of a log is that if I have, so let me just write here so you're seeing property 3 of logs, is that if I have, say, it doesn't matter what base, I'll just write ln for shorthand of, say, x to the k. what we've talked about is that K can come down and you can just have ln of x. And so what's happened, so you're seeing, is that K popped down in front. Now, if this isn't familiar, you might want to just look up the 3 properties of logs, because it's going to be quite useful in solving these kinds of equations. Okay, so what I'm going to do is just repeat the line above, and I will use the color red so you're seeing what is happening. As long as I do the same thing to both sides of the equation, that's okay. So I've just taken a natural log of both sides. You can use any log you want. I would suggest you use either natural log or log base 10, because those are the 2 that are going to show up on your calculator. And then for this problem, I chose natural log because I'm seeing an e. And natural log and e, when they're against each other, they're going to undo each other. They're inverse functions. So if I use my properties of logs that I have on the other side, what's happening is that is coming down in front. And I have k times 3 and then ln of e, that's on the left, and then the right is ln of 12 over 20. If you want to, it would be fine to reduce this. I think it will be 3/5 because both are divisible by 4. It's not really important because ultimately you're going to put it into your calculator or into Wolfram Alpha. Now remember, the thing that you wanted by itself is the k. So there's some stuff next to the k we need to deal with on the left. I want to just tell you ln of e is 1. The reason is natural log is really saying, hey, what power do you have to raise e to get back this e? And the answer is 1. If you don't want to think about it that way, you can just recall that those are inverse functions, so they're going to undo. So now I'm down to this point where I have 3k is ln of 3 over 5, and then the k is what I want. So what needs to go into Wolfram Alpha or on my calculator is the following. Okay, so let's see where we are with this. Okay, so using Wolfram Alpha, I've just put this into the computer, and what it's going to tell me is that I have a negative 0.170275, and it goes on and on and on. Now, in the problem statement, I was asked to round to 4 decimal places, and so I want to keep the following. I also want to make the point that we said at the beginning, because of the shape of the function, that it's decreasing as time goes on. We knew k would be negative because this is a decay model. So now that I have the k, the last thing to do for part A is just kind of put the pieces together. So the answer to A is the model. So we had C of t, and we have the 20 from the C sub 0, E, now we have this k value to the negative 0.1703t. And this is the model. So all the work on the last 2 slides was to generate this specific equation. And I just want to tie this into the graph. So obviously my graph is not to scale, but the curve that I have drawn in yellow is exactly what we've spent 2 slides finding. The formula for it is e to the negative 0.1703t. Now, what's nice about this is now that we have this model, we will be able to answer a number of other questions. I'll do the work on some subsequent slides, but let's just talk a little bit about what B and C are asking. So part B is asking, what is the concentration of the drug 30 minutes after it's administered? So they gave me T in hours, so I want to say that 30 minutes is 0.5 hours. And so I need to set T equal to 0.5 in my model. If I was just kind of tossing a point onto my curve, let's see, 0.5 is maybe like right there. So part B is asking me if T is 0.5, I want to find the Y coordinate or the C of T value that goes with it. So this is what part B is asking. We'll go ahead and do that. I just want to give you kind of a quick visual of what each of these parts is asking. So part C is saying the half-life, and we started with 20 as the concentration. So the half-life, it was saying when would you have half of 20, which would be 10. So it's saying, all right, that this value, let's say, is 10, and you can see that if I carry this line out, there's some point way out here, and again, my curve is not drawn to scale, but we're trying to find the t value. So this is what we're looking for, where our concentration in our blood is half of what we started with, or the 10. And so the key thing to pay attention to is that this equation, or this model, is letting us figure out the coordinate that's missing of both the green point and the purple point. You'll notice the green point is missing the second coordinate, and the purple point is missing the first. But we have everything we need to be able to find those missing pieces. So what I'll do now is just go ahead and do those problems for you. So we'll work on part B first. And as we've said, our plan is to get C of 0.5. So C of 0.5. And let's just remind ourselves so you can see where the different pieces are going. Our model is the following. And so what we want to do is wherever you're seeing the t, you're going to be putting in the 0.5. Like this. You can crunch this if you want, like if you're using a cell phone calculator, that's fine. But you can literally type this into Wolfram Alpha. And when I do, I get back, and it kind of keeps going. And then if you read the problem prompt, it's telling us how many units to keep. And I think we need 2 units after the decimal place. So we will round to the following. Or not 2 units, 2 digits. And then it's also going to be important to make sure we're answering with the proper units. Now, this is a problem about concentration. And the units of concentration that we were given were milligrams per liter. All right, so in 30 minutes, you started at 20, now you're down to 18 and something. So you haven't lost too much during that time. So it's a good idea not to take a second dose after 30 minutes of your Tylenol, for example. So part C has this question about half-life. And if you get a question that says, what is the half-life? What that really means is when do you have half of what you started with? And just to remind you, I will kind of do this fast, but we had this overall shape, and we were told in the problem prompt that you started with 20 milligrams per liter. And so half of that is the same as 10. So I'm setting C equal to 10, and I'm copying the model that I have at the very top of the slide. And now my job is find T. Now again, the t is trapped up in the exponent, so I'm going to go through a little bit of algebra to get the t by itself. So first I'm going to divide both sides by 20, so I'm going to have 1/2 is e to the negative 0.1703 t. Now just like before, if your variable is trapped in the exponent, a friendly log will help you get it down, and that's because the properties of logs make that very useful. Now, when a natural log and an e are right against each other, they're going to undo each other. So let me carry this over to the next slide and show you what I mean. So we have ln of 1/2 is equal to ln of e, and the e was raised to the negative 0.1703 t. So the shortcut is just cross them out, but what's really happening is properties of logs are letting this come down in front. And then ln and e, when they're against each other, give you back 1. So I have ln of 1/2 is negative 0.1703 t times ln of e is the 1. So this is great. The t is no longer trapped in the exponent. It's down, and t is the thing that you want to get alone. So if we divide both sides by whatever is next to the t, the 1 I'll just ignore, so I have the following. Wolfram Alpha is able to handle this, and when we put this in, we get back 4.07015 goes on hours. And reading the problem instructions, we're supposed to round to the nearest tenth. So I'll round like this, and then of course I want to give my units. So that is the answer to part C. Now let's go back to the original picture that we have. And I just want to point out that the missing piece in the purple point is now this 4.1. That seems reasonable. And the missing piece in the green point is this 18.37 that we found in part B. And kind of just as a quick check, let's make sure that those values make sense. To me, they do, because the y values are decreasing, and it seems reasonable that they are on that curve. And so that is kind of what the problem is about.